Okay, so we have a warm-up. Go ahead and do these problems. They're pretty much chain rule problems. For the first one, we have an outside function of cosine squared and then inside function of 3x squared. The 4 can just be factored out. Over here, this is x to the negative 6, and then inside we have 4x cubed minus 7. And over here, we have x to the 100, and then inside we have a cosine, and inside of that, we have a x squared plus 3. So this one right here will be a triple. So go ahead and give this a try, and we'll talk about it. So for the first one, we go ahead and do the derivative first. We look at the, and if you will, negative 4x, negative 4 times x squared, since the outside function is x squared. So we multiply the 2 by the negative 4, which gives me negative 8. Now we have the inside remaining the same, cosine 3x squared. And on the outside, we got to multiply by whatever is the derivative of the inside. The derivative of cosine is sine, negative sign, which is why we have a negative sign. Leave the inside the same, 3x squared. And then multiplied by the derivative inside of that, which is 6x, which is why we have this. By the way, prior I didn't notice that there was a squared right there. That too was hidden quite well. So this was actually a, it seems that this was also a triple, just like number 3. All right, for number 2, we have x to the negative 6. And we got to multiply it by negative 6 on the outside, make that negative 7. Remain the same inside. And then multiply by the derivative inside, which will be 12x squared. And when everything's said and done, you already took care of the negative exponent by moving into the bottom, you should end up with this answer right here. For number 3, same thing. Let's get started. So we have x to the 100. Move the 100 to the front, which is why we got this. Leave the inside the same. Multiply by the derivative of the inside, which is a chain rule inside as well. Cosine is negative sine. The x squared plus 3 remains the same. And then on the outside, you multiply by 2x, because that's the derivative of x squared plus 3. When you simplify everything, you should end up with this. So today we're going to find some applications of sine and cosine derivatives. They're great because they're oscillating functions, and there are many things in real life that oscillate, like a pendulum going back and forth or a spring. It has a lot to do with physics as well, so if you like physics, you're gonna like this. So let's graph this one. Well, the first thing I would probably look at is, oops, not that. I would look at the 3, because that's gonna move the graph up a little bit. You create a new fake x-axis, and then you just focus on graphing the sine function. Now, we also have to look at, let me use a different color, the 2. What the 2 will do, it will make the graph, it will stretch it vertically. So instead of alternating between 1 and negative 1, it alternates from 1 to negative 2. But because it was moved up 3, it will alternate from 1 to 5. Then we want to look at the inside, x plus pi. Now typically, when you have in the inside, when the shifting factor or number happens on the outside of a function, you move it accordingly. Like if it's plus 3, you move up. But when we talk about the inside, we do the opposite. So when you see x plus pi, you would think you move the function to the left, but you actually don't. You move the function to the right. So essentially, we move the sine function that now goes up and down 2 units, pi units to the right, which is why we have this fake y-axis on pi. At this point, you can start graphing the function. Essentially, it's the same thing as just regular pi. The only difference at this point, using the fake axis, of course, is you go up and down 2. Another thing to point out is that a sine function will start somewhere and it will end somewhere. After this point, it will repeat the exact same pattern. It's oscillating, which is why it's so awesome for real-life situations, such as pendulums. Here's some graph properties to know. So go ahead and take notes, but I'm going to talk about them real quick. So let's say we have a standard function like this, and this could be a sine or a cosine, which is why you see a sine above the cosine. What do each one of these represent? So when it comes to the c, it kind of tells you where the graph's going to start out of. So let's say we have an oscillating thing. We're going to talk about a pendulum in the next problem, where it's like a certain distance away from the wall, and then it goes to maximum. Let's say it starts at like 4 meters away from the wall, and it goes as far as 12 meters from the wall. What does C represent? Well, 4, 12, so that's like, what's the average between those? That's about 8, right? So C would be 8 in this case. So where is the center of this sine or cosine? When it comes to A, we talk about the maximum. How far from the center does the graph go up and down? So in this case, A, for the one that I just talked about, it goes all the way down to 4. The center is 8, so A in this case would have been 8. And then when it comes to the sine and cosine, you're very often not going to be asked to pick one. And it really depends on the situation. For instance, if it tells you that this graph starts from the center, then you want to obviously use a sine, because you know the sine. A sine tends to start from the center and then goes up to the maximum minimums, right? And if the center of the sine is the same, we know how sine behaves. It goes in the maximum at pi over 2. It goes to 0 again at pi. And then 3 pi over 2, it goes to -1. And then for cosine, you want to use that bad boy when cosine, when you start at the maximum. And then B represents the, how do they define B? B is the, does it not have a definition? Well, it doesn't matter. In order to get this variable, you follow this equation. Whatever period you're given, which represents how much time it takes for one cycle to happen, it might be 7 seconds, then you would have 7 seconds equaling 2 pi over 1 over b, and b has to be a positive value. And then d represents the phase shift. How much is this thing shifted left or right? For instance, they might tell you that we are starting off with a minimum at I don't know, 2 seconds, right? So minimum at 2 seconds, d would be in this case 2. And because we start at the minimum, not 0, you probably want to start with the inverse cosine. Cosine usually starts at the maximum, so if you start at minimum, you will put a negative in front of that a, and you would use a cosine. Alrighty, I hope that helped. Let's do some problems. Jack's beanstalk grows in sprouts. Okay, I don't like problems that have too much information, because now I don't know what beanstalk is, and then it grows in spurts. I don't know what spurt is. Its height, y feet, above the ground at time t hours. Since he planted, it is given by this function right here. You probably notice I'm not a good reader as well. Write an equation for the derivative, plot the graph of y and the velocity graph on the same screen. Use the window from about t equals 0 to t equals 10. Do there appear to be times when the beanstalk is shrinking? Justify your answer. Find intervals where the beanstalk is shrinking. Alrighty, so clearly we're supposed to use a graphing calculator based on how I just read it. So let's do that. So I went ahead and put the functions in there. As you can see, everything is in. And then I also took the liberty of taking the derivative. I didn't really do it on paper. I just kind of like did it in my head. So this is just chain rule. That's why the pi appears right here. And then sine is cosine. And then I didn't want to do this in my head, so I just did 12 divided by whatever the power was, 1.2. And then 1.2 minus 1 is just 0.2. So, also, if you noticed, oops, what did I just do? I just deleted something, didn't I? Okay, let's go back, and that is 0.2. There we go. I also took the liberty of, and you don't see it anymore because now it's activated, I took off that graph because I didn't want it. Now before starting this, I also messed with the window. They did tell me to go from 0 to 10, which is what I did. I just scaled it by 1, didn't want to have to worry about too much. And my y's, I did accordingly. So when you plug in 10 into the function, you get like 190 point something. So, and when you plug in 0, you get 0. So I did from 0 to 191. And that's how I ended up doing it. So let's graph it. That's what the function looks like. Now the question is, do there appear to be times when the beanstalk is shrinking? And I would say no, because I only see the function going up. But because it's such a large scale, which is 191, it could be that it is shrinking, but it's just hard to see with the eye. So what I'm going to do now is graph the I'm going to go ahead and activate the derivative, because if the derivative at any point is negative, that would imply that the height per second went down at some point. So as long as the derivative stays above the x-axis, I can be correct. So let's see. Ooh, you know what? I guess I was wrong. I am seeing, so let's go ahead and zoom in on that function. So let's go and let's go ahead and go negative 20, and let's go ahead and go 20. I'm just guesstimating right now. Okay, it's graphing the first function. You see that? It's loading. It's graphing the first function. Okay, now it's graphing the second one. Yeah. There are definitely times when the derivative is negative. Alrighty, finding out when it's negative is very easy, especially with the calculator. You pretty much go calc, find a 0, and then left bound. Where is it? Well, first let's do this. Let's go to the y. Let's deactivate this one because I don't care about that one. And now we have the derivative. And you can tell I don't really care if the entire function is on the graph, because I only care about when it's negative. Alright, calc 0 left bound. I have to go all the way to the first one because I like to do things in order. Okay, I don't actually need to see the dot because I can see the numbers. I know I'm on the left bound. Press enter. Go to the right bound. Press enter. Guess. So the first one is at 0.6364 all the way to, and then let's do the same thing. Can be a little tedious if you have to do it like all this times. Okay, left bound, right bound, and that's exactly why the left and right bound exists, because you have situations like this where you hit the x-axis so many times. Alrighty, so all the way up to 1.3399. Alrighty, I do want 3 decimal points, so round accordingly, and do this process again for all the other ones. Now, given that I've immediately forgot what the first number was and I'm trying to make a video, I didn't write it down, but you would simply, let's go ahead, I should have just written it down while I was, because I just realized I can actually write while doing this. So, given that the 0 doesn't tell me much, leave it as open parentheses, and then the first number, and then the number we just got, and then you want to unionize the next intervals. So do the same thing, and you should end up with an answer that looks like this. Come on, there we go. Let's say we have 1 area, 2, 3, 4, 5. Ooh, we need one more. And another one. Alrighty, so that's it for that problem. Just do the zero calc several times, 5 times to be exact. Actually 10 times, because you have to do the left and the right 0 in order to get the bound. Man, this is taking so long to finish. Sorry, I am so sorry for the length of this video. Okay, this is my second time recording this problem, and the reason is the first time it took me over 8 minutes to do. I can't have that. So let's go over the problem real quick. We have a mass bouncing up and down. You see it right here. It's oscillating. It's either going to be a sine or cosine. Time is t in seconds. The period is 1.6 seconds because making a complete cycle happens every 1.6 seconds. At 0.4 seconds, y reaches its greatest value, 8 feet. That tells us we're going to start with the cosine. And when you start with the greatest value, we're going to start with the cosine. And then it goes to smallest 2. So there's a lot of stuff you can figure out pretty much. So for 1, we have a cosine. Now, what values do we have that we're going to use? So pretty much our greatest value is 8 and our smallest value is 2. So the center happens in between. So in between, that would be 5, I believe. The reason why I know that is because 5 and 2 averages 5. If I add 8 and 2, that's 10, divided by 2 is 5. Okay, I'm making the video long again. From 5 to 2, that's 3, which means that's a 3 cosine. We start with the greatest value, so we're going to keep a positive 3 cosine. And then we need to find b, so period is 1.6. 1.6 equals, and then what was it again? 2 pi over b. Multiply b on both sides, divide by 2, but divide by 1.6. That's 2 divided by that. 2 divided by that, what is that? So I did the math real quick. It's 1.2 when you multiply b on both sides and then divide by, oh, dang it. It's 1.25 pi. Of course, nothing's going to be flawless. I'm always going to make mistakes. Alrighty, and then the phase shift. So notice how the t starts at 0.4. That means it's going to be t minus 0. Give me a break. 0.4. Alrighty, we just created part A. That's pretty much what you do. I guess this will be the hardest part of it. 5 is the starting point. Please go back to find out how we got the 5. And then 3 is the amplitude. This is the b value. And then this is the phase, how much we move the graph left and right. Our next one is finding the derivative. Shouldn't be too bad. You already know. The y is going to end up being 0. Then we have 3 times, and then negative sine. So minus 3 sine of the inside stuff times the derivative of an inside. That will be 1.25 pi. So I'm going to make this look better. Now I might have made a mistake. I kind of did some math in my head, but if I'm correct, that's the correct derivative. Just highlighting, just talking about it real quick. This went to 0. This remains the same. Then the derivative of this should be negative sine, if I'm not mistaken, which is why I have a negative here and then a sine. And then you have to then multiply by the derivative of the inside, which that should have given you 1.25 pi t. Oh, what did I forget to put? I'm about to put it. What did I forget? It's a pi. Alrighty. So the derivative here would have been 1.25 pi. And yeah, that's it. So I'm pretty sure I did it right. I might have made a mistake. I don't care too much if I made a mistake, because you guys know how to do derivatives. So if I did make a mistake, you guys can correct me. And then put in the numbers. So I just plugged in the values into, let me just go ahead and use my, mom, I never prepared. I plugged in these values into this equation right there. And then I did the same thing with this and this one. And I got these values. So go ahead and do it yourself and see if you get the same things. Now, part D is asking, at 2.7 seconds, is the mass moving up or down? Just for your answer. 2.7, that's a negative. Therefore, it would be, all right, here's the thing. What does D represent? D represents the distance from the ceiling. So if D has a positive, if D has a positive growth, meaning the derivative is positive, rate of change, then it means it's going away. If it has a negative derivative, it means it gets closer. So is it moving up or down? It is moving up because the derivative is moving up because the derivative is negative. Because the growth, the distance has a negative slope, that implies that the distance is declining. I hope that made sense. What is the fastest the mass moves? Where is the mass when it's moving this fast? What's the amplitude of this bad boy again? It's 4.75 pi. So whatever that is. So 4.75 pi will be the amplitude. And when is it happening? We're talking about a sine, right? When is sine, so in order to get that positive value, first of all, how do you interpret the fastest shouldn't matter whether it's positive or negative, because we're just talking about speed. But assuming we want the positive value, then you probably want to find out when 1.25 pi times t minus 0.4, everything that's inside of right here, when does this thing equal 3 pi over 2? And the reason why I say 3 pi over 2 is because if you look at this equation again, I'm going to use my highlighter. I'm creating too many errors. If you look at this equation again, it's a negative up front. There's a negative, which means that I need sine to be negative in order to get a positive velocity. So for sine to be negative, I need 3 pi over 2. So you just pretty much solve this out. So let me do that. So I just did the math, and the answer that I got is t equals 1.6 seconds. And then, since we don't necessarily care, I think that's a cockroach right here. Since we don't necessarily care if it's a positive or negative speed, you can do the exact same thing with pi over 2. So you can actually take this guy and do pi over 2, and as long as t is positive, you should be fine. Now that's how I interpret the sentence fastest the mass moves. So I don't think if you're looking for this one, you probably are looking for the time when it's pi over 2. But I'm trying to consider what if they're saying that it's a positive velocity is indeed greater than the negative velocity. Alrighty, let's move on. So let's do another problem. A pendulum hung from the ceiling makes a complete back and forth swing each 6 seconds. As the pendulum swings, its distance d in centimeters from the wall of the room depends on the time t seconds. Since it was set in motion at time 1.3 guessing seconds, d is at its maximum of 110 centimeters from the wall. The lower bound of d is 50 centimeters. Assume that d is a sinusoidal function of t. Alright, so let's do this. So I thought over here I'd kind of break it up a little bit. So far I just wrote down that we have a d equaling, and then the reason why I picked 80 is because the average between 50 and 110 is 80. It's the midpoint. And how far away is the middle from each extreme? That would be 30. Now, why did I choose cosine? The reason why I chose cosine is simple. We're talking about a maximum. So at 1.3 seconds, we're going to use this number, we were at a maximum. So let's see where it says that. Where did it say? As set in motion at its maximum. Okay, it was literally the next few words after. So since we start with a maximum, I want to start with the cosine. Cosine tends to start with a maximum. Alrighty, so we now are trying to find out what the next number is, and we start off with writing down the period equals 2 pi times 1 over b. And when all is said and done, you're going to have 3 over pi over 3. So the number that we're going to put next is pi over 3. So let me go ahead and do that. So what have I done? I pretty much solved for b right here. Put that value in here, and then I have t, and I put minus 1.3. The thing is, I'm choosing this to be the starting point because that is like a maximum for cosine. The starts at the maximum. So since that's to the right of the origin, I put a negative because remember, inside we do the opposite. When the graph was moved to the right, that means that in between the variable and the face thing, it must be a minus. So this is a little awkward because I actually don't remember where I left off before I paused the video. So I'm assuming I talked about this equation completely. Please correct me if I'm wrong tomorrow. But then the next thing was write the equation for the derivative. So I took the derivative, the 80 goes away, that goes to 0. The cosine becomes a negative sign, which is why we have a negative. We have a 30, and then the sign, leave the inside alone, multiply by the derivative of the inside, which will be pi over 3. So that's the derivative. Now it's asking us, how fast is the pendulum moving when t equals 5 seconds? I did this calculation and got this, and then when it's 11 seconds. That was a little confusing, because I know the period is 6. So if 5 is 21.021 centimeters per second, then 11 is 21.021 centimeters per second. Sines and cosines repeat each other. And if you are trying to find answers, which is exactly a period away from the previous number, it's the same. Guess what the answer is going to be for 17? It's going to be the exact same thing. However, it would have been more interesting if this had been like a 12 or 13, then actually have to plug it in. But if you're going to ask me what it is at -1 second, 5 seconds, 11 seconds, 17 seconds, 23 seconds, or 29 seconds, which is just 6 seconds away from one another, which is exactly the period, it is not interesting. The answer will be the same all the time. Why, you ask? Because it's oscillating. It is repeating itself every 6 seconds. For the next one, saying if you plug in t equals 20, is the pendulum moving towards the wall or away from the wall? Explain. Well, for that one, gotcha. Yeah. Alrighty. Let's go back to the thing. What does d represent? As the pendulum swings, its distance d in centimeters from the wall, from one wall of the room, depends on blah blah blah. Alrighty, so d represents the distance. Now I already plugged in what happens when you have 20 and you end up with an answer which is negative, it doesn't matter, oh, well, it's actually negative 21.0221 centimeters per second, but it doesn't matter. Because when you have a negative, that means that your distance is decreasing. You're going towards the wall. You're going towards the wall. I am so glad I'm not editing out any mistakes I make while talking. Alrighty, E. Letter E. Let's do that one. So, now we have to find out what's the fastest the pendulum swings. And that's fun to find out. And where is the pendulum when it swings the fastest? Alrighty, was getting kind of loud, so I kind of had to stop the video. When it swings the fastest, it's negative 30 times pi over 3, so negative 10 pi, whatever that is. Negative 10 pi and centimeters per second. Now, since you're the student, you know what I want. I want 3 decimals, so don't leave it as negative 10 pi. What's the first positive? Oh, what's the fastest pendulum swings? Where's the pendulum when it swings? Okay, where is it? Well, first of all, that's the fastest is 10 pi. We want for the speed, so we don't really care for a negative. 10 pi would be sufficient. With 3 decimals, of course. But where is it when this happens? Now, in the previous problem, I did talk about the issue of fastest, what it means. For a physics teacher, I would have not cared about negative, positive. So when does it happen? It happens when sine equals 1 or negative 1. So you're going to let pi over 3 times t minus 1.3 equal pi over 2. Yes, pi over 2 or 3 pi over 2. Just for funs and giggles, we're going to let it equal to pi over 2. So let me just zoom in amazingly. So pi over 2 equals, and I completely forgot what I'm talking about. Pi over 3 t, pi over 3, and then t minus, and what was the face thing? 1.3. 1.3. Whee! Alrighty, so you pretty much solve that out and see what you get. So I get 2.8 seconds, and I did pi over 2, by the way, so the inside equals pi over 2, which means that sine would have been a positive one. That would have given you exactly the negative 10 pi. To get the, let's undo that. To get the positive 10 pi, you would simply let it be 3 pi over 2, equaling the same thing, and then you pretty much do this. You do the same process, whatever that is. And then, what is the first positive value of t at which the pendulum is swinging 0 centimeters per second? Where is the pendulum at this time? When does sine equal 0? Let's see. You let that equal to 0, then that would be, wouldn't that be at 1.3 seconds? Yeah, it's 1.3 seconds. So I just look at the inside. I know how sine behaves. So sine starts at 0 and does this thing. So I pretty much know that the beginning of sine is 0. So as long as I pretty much find out what makes the inside 0, I pretty much find out what I'm looking for. So the answer will be 1.3 seconds. Alrighty, that's it for the video. Sorry it took so long. My deepest apologies. See you guys tomorrow.